Subtraction, y'all. Okay, so we're recording now. All right, you guys, we're going to start today with 7.4. So I'll tell you what, let me go through 7.4, and then I'm going to pull up I'm going to go to our Blackboard page, y'all, and I'll pull up what I have under the weekly activities. But the notes here for 7.4, they're in that folder, y'all, for week 11. So we're going to talk a little bit about vectors. Okay, so how do we interpret vectors geometrically? So scalars are quantities that are described, by a single value called the magnitude or the length, the size of the measure, okay? And then vectors are quantities that describe both by magnitude and direction. So by magnitude, guys, we mean length. And so we got an example here, and it says the speed of an object is a scalar quantity that tells us how fast an object travels. The velocity of an object is a vector quantity because it tells us how fast the object travels and in which direction. So it says a vector in the plane is a line segment with a specified direction. So let me see, let me get my pen here. Whoa, buddy. Let me get my pen here. And so here's our vector. We have what we call an initial point where we're starting and a terminal point where we end. And you can see, y'all, there is a little arrow right there. And that's just letting us know that the direction is starting from P and ending at Q, okay? So the vector PQ is an arrow with endpoints P and Q pointing from P to Q. P is what we call the initial point of the vector. Q is what we call the terminal point of the vector. So the magnitude of PQ, and this is what we use to denote it. It looks kind of like absolute value, but they're like double bars. Is just the length of the vector. Okay, so it says using the context of placement of an object, the vector PQ refers to the object's overall change in position and moving from point P to Q. So it says two vectors are equal if they have the same magnitude, meaning they have the same length and they have the same direction, okay? So here it says the vectors in the figure are all equal to the vector AB. So if you notice over here, y'all, all these vectors here, they are all equal to the vector AB because they have the same length and they're all going in the same direction, okay? So it says for vectors, we often use boldface lowercase letters such as U, V, W. And then it says if V is equal to the vector AB, then V represents the set of all vectors equal to AB, okay? All right, so we're going to figure this out. It says determine if the two vectors are equal. So when they're saying that, y'all, this is what we're looking at. These two vectors right here. So we're going to go from the point -3, 1 to the point 1, 4. So here's my XY axis, right? If I want to find the point -3, 1, that's going to be 1, 2, 3 to the left and 1 up. And then 1, 4 is going to be 1 to the right and 1, 2, 3, 4 up, okay? So this is the vector V, okay? So all I did is just plot those 2 points, and I'm going from -3, 1 to 1, 4, so you can see that's why my arrow is pointing like upward, right? Okay, let's do the same thing from 0, -3 to 4, 0. So 0, -3 is going to be 1, 2, 3 down, and 4, 0 is going to be 1, 2, 3, 4 to the right. Okay, so remember what we're trying to figure out. If the two vectors are equal, they're going to be equal if they have the same length and if they're going in the same direction. Guys, let me ask you a question. You can just eyeball this. Does it look like they have the same length? Yeah. Are they going in the same direction too? Yeah. Okay, so these two vectors here, y'all, are going to be equal. Yes, exactly. Exactly. You could just do the rise over the run. That's right. Perfect. Okay, now let's do the same thing for the next one. So look, we're going to do here, we're going to plot, and working again, -4, 2 to -1, 4. Okay, so -4, 2 is going to be 1, 2, 3, 4 to the left and 1, 2 down. And then -1, -4 should be 1 to the left and 1, 2, 3, 4 down. So everybody agree that's what that vector looks like? Okay, and then let's do the next one, from 4, 2 to 1, 4. So 4, 2 is going to be 1, 2, 3, 4, and then 1, 2 up. Okay, and then 1, 4 is going to be 1 to the right, and then 1, 2, 3, 4 up, and it's this vector right here. Okay, so now guys, I'm looking at the green vectors. We want to know if they're equal. Number one, do they have the same length? Just look at the picture. What do you think? They got the same length? Okay, do they have the same direction? No. Okay, these vectors are not equal. They have the same length, but the directions are not the same. And in order for them to be equal, they have to have the same length and the same direction, okay? All right, so let me keep scrolling over here and see what else we can find. Okay, so it says if vector V represents the displacement from P to Q, and vector W displaces or represents the displacement from Q to R, then the vector V plus W represents the displacement from P to R. Okay, so let me explain what this means. We can think about it really, really easy though. When you're a kid, you're going to go over to your friend's house. The neighbor has a fence, so you have to walk on the sidewalk from here to there, and then from the sidewalk to there, right? There's a method called the tip to the tail. So if I take the tip of the vector V right here, and I put the tail of vector W starting in that same direction, which is how it was drawn, you were to say, look, if my neighbor didn't have a fence, couldn't we have just cut across like that? And that's the vector V plus W. Okay, that's really all it is. So again, if you think about it, when you're a little kid, you're going to go to your friend's house, right? It's cutting through somebody's yard. That's exactly what it is, right? Okay. Now, there's another way to go about doing it, and the other way going about doing it is starting from this here, y'all, is what we call the triangle method. Because you can see we got a triangle, right? Or they call it the tip to tail. I like the tip to tail. I think the tip to tail works. And it's just like John said, it's like you're cutting through somebody's yard. If I was going to walk from P to Q and then from Q to R, we could just walk from P to R, right? Now, this is called the parallelogram method. The parallelogram method says, well, if you put both vectors V and W starting at the same point, then when you add them, what you basically do is you make a parallelogram. This vector here is the same thing as vector V. How do I know they're the same? They have the same length and they're going in the same direction, right? And then this one right here, y'all, would be the same thing as the vector W. How do I know that? They have the same length and they're going in the same direction, right? So if I do that, there's another W. You see what I'm doing? I'm making like a parallelogram here. Then V plus W is what happens when you draw the diagram, okay? That's how you can do V plus W. I like the triangle method because I think the triangle method is like more intuitive. Like we said, you know, you're cutting through somebody's yard. If you're going to go from here to here and then from there to there, you can just cut across, okay? But they both mean the same thing, okay? Let's see. So they're both ways to visualize adding two vectors, like geometrically, okay? And if you notice here, remember when I said, look, if I think about this vector right here, John, this here is the same thing as the vector W because here was W, and this vector has the same length as that one, and it's also in the same direction. I'm going back really, and I'm kind of doing my triangle method again, right? If I'm going to go from here to here and then from there to there, we could have just gone that way. Well, you're not necessarily doing the Pythagorean theorem because we don't necessarily know that this angle here is a 90-degree angle, right? We're just saying what happens if we were to, like you said earlier, you're just cutting across. That's all it is, right? The angle isn't necessarily important, but you're really just finding that diagonal there. Okay, so guys, have the same thing when we talk about vector subtraction, okay? So again, if here is my vector v, and here's my vector w, I want you to notice what negative w looks like. If this is w, negative w is going same length, but the opposite direction, okay? So if we were gonna go from here to here, and then from here to here, we could have just gone this way, and that's v minus w, because remember, v minus w is the same thing as v plus a negative w, right? And how do we add vectors? I go from the tip to the tail, and from the tip to the tail. So if I'm going to walk from here to here, we could just use that triangle method again, okay? All right. So let's take a look here at some of these problems, and it says if a vector v is multiplied by a real number k, then the magnitude of kv is the absolute value of k times v. The direction of kv is in the same direction as the vector v as long as my k number is positive, and it's in the opposite direction if my k number is negative, okay? So just to kind of show you again, here's my vector v. Look at 2v. 2v, same direction, it's just twice as long. Half of v, same direction as v, it's just half as long. Look at negative 2v. It's twice the length of v, but now it's in the opposite direction. And the same thing for this one over here, the negative 1/2 v. It's half the length of v, but again, going in the opposite direction. Okay. All right. So let's take a look here. It says a vector sketch with an initial point at the origin of a rectangular coordinate system is said to be drawn in standard position. All right. So let's take a look at this problem here, see if we can't figure it out. It says sketch u plus v by placing the initial point of u at the terminal point of v. Okay, so just to let you know, y'all, that's the initial point of u. That's the terminal point of v. Okay, so I want to draw that vector u, that red vector, I want to draw it exactly as it is, except I'm going to just move it over to where those two green points coincide. So look, let's do it like this. Let's see. I want to figure out what my triangle here is going to look like. I'm going to go 1, 2, 3, 1, 2, 3. Okay, so do y'all agree I could do this? 1, 2, 3, 1, 2, 3. Okay. So think about what we're doing. We were originally walking from here to here, and then from there to there. So u plus v would be that vector right there. So far, so good? Right? All right. So now let's take a look at number 3. Number 3 says sketch u plus v by drawing u and v with the same initial point. Okay, so I'm going to do the same thing here, y'all. I'm going to figure out how long this, what my triangle for my vector u is going to look like. I'm going to figure out how many spaces I need to move. 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3. Okay, so I can see that my u triangle has a length, going down like a vertical distance of u and a horizontal distance of v. We want to start them with the same initial point. That means that this point right here, y'all, and this point right here are going to be the same. So I'm just going to count. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. Okay. All right. So now that we have that there, if we're trying to find what is u plus v going to look like, this here, y'all, is where we're going to draw like our parallelogram. So do you remember from here, I went down 8 spaces and over 3? I'm going to do the same thing here. Look, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. And was it 4 spaces over? 1, 2, 3. Well, look, 1, 2, 3. Am I good? I'm going from here. 1, 2, 3. Because look what I'm doing. All I'm doing is I'm going down 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. You said I'm done? You said I'm done? Okay. Then I'm going to do the same thing here. I'm just going to connect those two right there. And then remember what the u plus v looks like, y'all? It's the diagonal. So what I have there in green is that u plus v. And that's called the, that's like the parallelogram, right? Which one do y'all think is more intuitive, the triangle or the parallelogram? Which one makes more sense? Do they both make the same amount of sense to you? Did neither of them make sense? I'm just curious. Anybody? Triangle is a little bit more, right? Because it's like John said earlier, it's like you're cutting through somebody's yard, right? I like the triangle method too, y'all. I think that one makes the most sense. But and that's kind of what I'm doing. Like even when I'm doing the parallelogram method, if you notice, look, we put them with the same initial point, right? But then we drew this one over here, and that's like I tip the tail of going back to the triangular method. You know what I mean? So yeah, I always go back to the triangular method. I just think that one's easier. Okay, so let's see. Let's take a look at this one. It says sketch v minus w by drawing v and w with the same initial point. Okay, so look, we're going to draw w with the same initial point as v. So first thing I'm going to do, y'all, I'm going to figure out how many spaces I need to go to get to my w vector. I'm sorry. So this is 1, 2, 3, 4, 1, 2. So I'm going to go 1, 2, 3, 4, 1, 2. 2, 3, 4, 1, 2. Yeah. Okay, so this right here, y'all, is my vector w. Let me ask you a question. What would negative w look like? Anybody know? So this is w right here, going like that. What do you think negative w would look like? The opposite direction. So do you agree with me? I would go 4 up, right? 1, 2, 3, 4, and then 1, 2 to the left. So wouldn't negative w look something like this here? Right? And couldn't I put that negative w, y'all? Couldn't I put that negative w over here as well? Let's see. 1, 2, 3, 4, 1, 2, like this. Couldn't I do that? So if I wanted to draw v minus w, remember what that would mean? Here's this here, y'all, is my negative w, right? So I'm going to go from here to here, and then from there to there. Couldn't we have just done that to begin with? There's my v minus w. Guys, let me ask you a question. Do you agree with me that this would also be v minus w? Because it's the same length and it's going in the same direction. Does that make sense? All right. Let's take a look here at number 5. Number 5 says we're going to sketch negative 2v and 3w in standard position. Standard position just means we're going to be starting at the origin, okay? So look, let's look at my vector w. It is 1, 2, and 1, 2. So 2 spaces to the right, 2 spaces up. But we don't want to just do w, we want to do 3w. So 3 times that amount. So instead of me going 2 spaces to the right, how many spaces to the right would I need to move? There you go. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And it's going to look like this. And this right here, y'all, would be, there you go. Because it was 2 spaces to the right and 2 spaces up, and we're doing 3 times that amount. It's going to be 6 spaces to the right, 6 spaces up. Okay, let's take a look at V. So from my starting point, I'm going to go down 1, 2, 3, and then 1, 2. So it's 3 spaces down, and it's 2 spaces to the left. Okay. But now we want to find negative 2V. So we're going to go twice the distance, but opposite direction, right? So if I was going 3 spaces down, but now I'm going to go twice that distance, but in the opposite direction, how many spaces am I going to go up? But remember, I'm doing twice that distance though, right? So what's 6? So we're going to go 6 up. So starting from here, we're going to go up to 6. And then if we were going to go originally 2 spaces to the left, but now we're going to double it, but in the opposite direction, we need to go how many spaces? To the right? There we go. And this here, y'all, would be our vector negative 2v. Let me ask you a question. Aren't we just counting? Isn't that really what I'm doing? I'm just counting here, right? You know how to count. Okay, so let's take a look here, y'all, and see if we can figure out how do we represent vectors in what we call component form. So it says, let P be the point x1 and y1, and let Q be the point x2 and y2. The vector PQ in component form is given by, and look at the notation they have here, y'all. They say that V is x2 minus x1, comma y2 minus y1, but they don't put parentheses. They kind of put like these little angles, or I don't know what you would call them, like little arrows or something like that, okay? So, and it's just to denote, I'm sorry? Obtuse angles, yeah. And it's just to denote this is vector notation, okay? So it's not the same thing as point notation, very similar, but it's not exactly the same. Okay, so look, it says given vector V with initial point 3, 8 and a terminal point negative 1, 3, find the component form of V. So look, y'all, this is my x1 and my y1. This is my x2 and my y2. So the way we're going to write our component V is by using this formula here, x2 minus x1, comma, y2 minus y1. And so we're going to take those numbers and we're going to do a little plug and chug. So x2 minus x1 is going to be negative 1 minus 3, comma, y2 minus y1 is going to be 3 minus 8. And so this is going to be negative 4, comma, negative 5, using our vector notation. All right, so number 7 here says, given vector V with initial point 12, 12, negative 10, and terminal point negative 20 and 10, find the component form of V. Okay, same exact problem. So I'm going to call this my x1 and my y1. I'm going to call this one here, y'all, my x2 and my y2. So I'm just going to use the same formula that we had before, x2 minus x1 and y2 minus y1. So let's go through. We're going to do a little plug and chug here. So our x2 is negative 20 minus my x1 is a 12. My y2 is a 10 minus my y1 is a negative 10. So this is going to give me negative 32, and everybody agree minus and minus makes plus, positive 20? John, am I doing okay? Right here, I had, let me fix this. Yeah, it was an x minus a negative 10, and so minus and minus make it plus. And that's how I was able to come up with a negative 32 and a positive 20. So far, we good? Okay. So there's a second part to question 7, y'all, and it says if V is placed with an initial point of 5, 3, what's the point of V? Okay, so we're talking about this vector right here. So remember how we came up with this part here? We said that x2 minus x1 was equal to a negative 32, and we said y2 minus y1 is equal to the number, positive 20. And all I'm really doing here, y'all, is I'm just setting this part equal to the first number and this part equal to my second number. Now, they're giving me an initial point. So they're giving me a value for our initial point. Now, remember, y'all, the initial point, those are the values for x1 and y1. So this is my x1 and this is my y1. So what this here is telling me is that x2 minus x1, which is 5, is equal to negative 32. We're trying to find the terminal point. So we're trying to find the coordinates of the x2 and the y2. If I'm trying to get the x2 by itself, how would I get rid of that minus 5? Okay, add it to the negative 32. And so we come up with x2, positive or negative? Negative 27, very good. Okay, we're going to do the same thing here, y'all. The y1 is equal to the number 3. So I'm going to go y2 minus 3 equals 20. So everybody agree we're going to add 3 to both sides? And 20 and 3 is 23. So our point x2 and y2 is the same thing as negative 27 and 23. Because it's a terminal point, y'all, look at the notation that I'm using. I'm using, like, writing it as a point with parentheses. The only time that I use, like, those kind of arrows is when we're writing the vector in component form. Okay? Yeah, that one right there. Okay, so let's take a look at the next part here, y'all. And this is talking about how do we perform operations on vectors in component form. Okay, so the first part here we have if vector V in component form is A1, B1, and vector W in component form is A2, B2, then V and W are the same only if A1 is equal to A2 and B1 is equal to A2. Okay, and let's see. If we have the same vector a1, b1, and the other vector a2, b2, look how we add those vectors together. We just take the x components and we add them, and we just take the y components and we add them. And we do the same thing if we're going to subtract them. And if we multiply them by some kind of scalar, some kind of value, all we do is multiply each of the components, like we did right now when we drew the pictures, right? So we said if one vector was, we had to go 2 to the right and 2 up, and now we're going to go 3 times as much. We got to go 6 to the right and 6 up, that kind of thing. Okay, so let's take a look here. Let's see if we can add or answer these questions 8, 9, and 10. So look, question number 8 says, let's take the vector r and add the vector s. How are we going to do that? By adding each of the components. So I'm going to take 1 plus 2, comma, negative 4 plus 3, and that's just going to give me 3 and negative 1. And there's my vector r plus s. Okay. All right, let's do number 9. Number 9 says we want to find negative 4s. So we're just going to take negative 4 times each of the components that we have here. So negative 4s, anybody know what it's going to be? There you go. You got it. Take it away. So let's take a look at number 10. It says 3r plus 2s. So the first thing I want us to find, y'all, let's find the vector 3r. Okay. So 3r, everybody agree that would be 3 and negative 12? Because all I'm doing is I'm taking this vector r and I'm multiplying each of the components by 3. And then if we were going to find 2s, wouldn't that be 4 comma 6? Because all I did is take these components and multiply them by 2. And so now look what we're going to do with those two vectors. We're going to add them together. So 3r plus 2s, anybody know what that's going to give us? There you go. And you got it. Let me ask you a question. What are you guys thinking about vectors so far? Easy greasy cover girl? Yeah? So far? So far, like, hey. So far, we're like, hey, vectors. I think I like vectors, right? Vectors are pretty cool. They're easy to do. So far, they are, right? Okay, let's take a look here. So far, right? Well, let's see. I mean, who knows? You know, maybe it's going to be so far, and then we're going to finish with 7.4. And you're going to be like, hey, let's take a test on vectors because I'm ready for this, right? All right, let's see. Maybe not. Maybe it won't be like that. I don't know. We'll see, guys. Okay, so a couple of things here. First thing is we have something called a unit vector. A unit vector just means it's a vector that has a length of 1, okay? Or magnitude of 1. Magnitude, length, same thing. I'm sorry? Magnitude is just length. It's not the direction. Okay, it's just the length. So we're gonna figure out how we do direction in a minute. Okay. So let's take a look here. The magnitude of the vector AB is just the square root of a squared plus b squared. That looks very much like Pythagorean theorem, doesn't it? Like the length, like the r, the way we find our r. Same sort of thing, right? Look at the notation they use, y'all. It's kind of like a double absolute value. But again, when we were finding the r, we were always taking the positive one, right? It's the same sort of idea here. Okay, so how do we find a unit vector in the direction of a given vector? So if b is a vector AB, then the unit vector, and this is the notation we use, u with the little subscript of b, in the direction of b is given by, and they have this little notation. So 1 divided by the magnitude of b times the vector b itself, which is just each of those components divided by the magnitude of the vector. Okay, so let's take a look, see if we can figure out how to do this problem here. It says find a unit vector in the direction of w and verify that it's a unit vector. Okay, so the first thing we need to do, we need to find the magnitude of w. Okay, the way we're going to do this, y'all, it's just going to be the Pythagorean theorem. We're going to take the square root of each of the components being squared. So negative squared plus 15 squared. Okay, negative 8 when we squared, anybody know? 64, very good. What about 15 squared? Anyone know that one? 225. Okay, very good. All right, let me grab my calculator real quick because I don't know what those are when we add them together. Turn this on, clear it out. 64 plus 225 is 289. Very good. So 289. And then I don't know if that's a perfect square or not, but we're going to find out. Is it? Second square root of my answer, 17. Nice and neat. There we go. Okay. So I want to show y'all something right here, y'all. Look what it says. The way we're going to find a unit vector in the direction of b, this is what we're going to do. We're going to take the a and b components, and we're going to divide it by the magnitude of that vector. So what we would do here is we would write uw equals, and I'm going to write it like this. Remember, my number a was what, a negative 8? I'm going to put that over 17. Our number b was a 15, and we're going to put that over 17. and there's our unit vector, and the direction of W. All you gotta do. Yeah, it's just fraction. So notice right here, that's all I'm doing, right? I'm taking each of that A value and that B value, and I'm dividing it by what the magnitude was, right? And this is what we call a unit vector. Remember what a unit vector means? That the length of that vector is going to be equal to what number? 1, right? So if you were to find the magnitude of this here, y'all, it should be equal to the number 1, right? And we could go through the whole calculation, but it's going to be equal to 1. All right. Okay. So the next part I have here, y'all, talks about, it says 2 important unit vectors are I, which has components of 1, 0, and J, which has components of 0, 1. These are what we call unit vectors in the direction of the positive and XY axis. Okay. So the representation of V in component form A plus B, or A and B, I'm sorry, in terms of I and J, this is how we write it. V equals AI plus BJ. Okay, so the I, y'all, is going in the X direction, and the J is going in the Y direction. And the values A and B are what we call the scalar horizontal and scalar components of V. Okay, so it says, look, let's write -12, -30 in terms of I and J. So look, y'all, what we're going to do here, we're going to call it V equals. If I do a little stare and compare, and I look at this and I look at this, I'm going to say, look, my A is the number in -12, and my B is the number in -30. And we want to write it so that it looks like this. AI plus BJ. So we're going to say -12 I minus 30 J. And that's how we write our vector in terms of I and J. I'm sorry? No, when it's like that, if you notice right here, it doesn't have the little component form, right? Because this is in the A and BI form. Okay, so it says relate component form and direction and magnitude of a vector. So given a vector in standard position, the direction angle theta is measured counterclockwise from the positive x-axis over the interval from 0 to 2 pi, or from 0 degrees to 360 degrees. Okay, let's see, magnitude, direction, components of a vector. So here we go. Let AB be a vector in standard position. Let our theta be between 0 and 360 in the direction of B measured counterclockwise from the positive x-axis, okay? So, look, y'all, B is the square root of A squared plus B squared. Tangent of my angle is equal to B over A. Again, we've talked about some of these things before, right? We're sort of seeing some of the same ideas kind of repeat themselves here. And take a look. How do we have the component of A? It's the magnitude of B times the cosine of my angle. And B is the magnitude of B times the sine of my angle. Isn't this very similar to, like, the X component is R cosine theta and the Y component is R sine theta? It's the same sort of idea, right? Okay, so here it is in component form, and here it is in the and the IJ form, okay? So let's take a look here. It says, write the vector V in the form AI plus BJ, where V has a magnitude of 10 and the direction of angle theta is 3 pi over 4. Okay, so we want to write it in this form right here, y'all. Okay, so V equals AI plus BJ is going to be equal to the magnitude of V times the cosine of our theta plus the magnitude with an I, and it's not the imaginary I. Yeah. Magnitude of V times the sine of my angle with a J. Okay. Yeah, and I'm just doing this part right here, John. Okay, so we already know the magnitude is 10. So this is going to be 10 cosine. Our angle here is 3 pi over 4 with my I plus 10 sine 3 pi over 4 with our j. And so y'all, the first thing I'm going to do here, y'all, is I'm going to pull up my little chart. Here we go. This is the one that I want to get. There we go. Let's open this thing up. Okay, this is what I'm looking for. And we're looking at 3 pi over 4. So here's 3 pi over 4. We're looking for the cosine and the sine. So the cosine is the negative square root of 2 over 2, and the sine is the positive square root of 2 over 2. So all I'm going to do right here, y'all, I'm going to say the cosine is the negative square root of 2 over 2 with my I, and the sine was the positive square root of 2 over 2 with my j. And let's see, won't this 2 reduce into that 10 and give me a 5 here? So I'm going to have a negative 5 square root of 2 with an I. And this 2 will cancel, and that 10 also give me a 5 plus 5 square root of 2 with our j. And we were able to write the vector in AI plus bj form. So y'all, I don't know about you guys, but I like having this little chart handy because it's usually pretty helpful. I can figure out those values nice and neat. And I mean, like John, your calculator, I know you have like you have the Inspire, right? When can you do me a favor if you have your calculator with you? Can you type in like say cosine of 3 pi over 4? So make sure it's in radian form. When you type in cosine of 3 pi over 4, does it actually give you the negative square root of 2 over 2, or does it give you a decimal? Okay. Uh-huh. Cosine 3 pi over 4. Does it give you, uh, did it give you negative square root of 2 over 2, or did it give it to you, and it gave it to you exactly like that? It didn't give you a decimal form? Okay. So, y'all, I guess it's all going to depend on what kind of calculator you have. So, like, if obviously, if I'm using this one here, and I think my calculator, I don't even know what mode I'm in right now. Let me check. Okay, I'm in radian mode. That's fine. So let me do it here. Cosine of 3 pi over 4. And so mine gives me, this is an 83 plus my notation, right? And so if you notice in the problem here, y'all, I'm not looking for the decimal notation. We're actually looking how to write it, exactly like this. So just, it's all going to depend on what kind of calculator you have, That's why having that chart, for me, at least for me, comes in pretty handy. Okay, so let's take a look at number 14, y'all. Number 14 says, find the magnitude and direction angle for S is equal to 7i minus 3j. Okay, so we know that S is 7i minus 3j. We need to first find the magnitude of our vector. I'll use S because that's the vector that we got. So remember, the way we're going to find the magnitude is we're going to take 7 squared plus negative 3 squared. So let's see, 7 when I squared I know is 49, and 9, or negative 3 when I squared is going to give me 9, and 49 and 9 should give me something like 58, and I can't actually break this one down, y'all, just to give you a heads up. 58, I can divide it by 2, but it's 2 and 29, and 29 is one of those prime numbers, so I can't break down 29, you know what I mean? So I'm just going to have to leave the square root of 58 as it is, okay? Now, we found the magnitude. We also want to find the direction angle. So let me just scroll back up here, y'all, so we can see how do we find the direction angle. Look what it tells me. It tells me the tangent of my angle is equal to b divided by a. Okay, so it tells me that the tangent of our angle is equal to the b value divided by the a value. B would be what number? What kind of 3? Negative 3, right? Good, negative 3. And a would be the 7. Okay. So in order to find theta, we're going to take what? The tangent inverse of negative 3 over 7. And so guys, one thing I want to mention here, if you look at the problem here, it's telling me that theta should be between 0 and 360 degrees. So we're going to write our answer in degrees, okay? So the first thing I'm going to do, I'm going to change my calculator to degree mode. Over, there we go. Okay. And we're going to go second tangent inverse of negative 3 over 7. And I'm coming up with, it's telling me to go to 1 decimal place. So y'all, would I write negative 23.1 or 23.2? 0.2, right? Okay. So, oops. So theta equals negative 12. Theta equals negative 23.2 degrees. Let's see, what quadrant are we in, y'all? Look at our, we're in the 4th quadrant, right? So if I was going to write that, because it does want me to write it between 0 and 360, wouldn't we just say add 360 to that? So I would be coming up with 336.8. So we found our magnitude and we found our direction angle, right? Okay, let me zoom in here a little bit and let's see if we can do number 15. So number 15 says a baseball is thrown with a speed of 65 miles an hour at an angle of 12 degrees from the horizontal. Write the velocity vector at the time of release in terms of I and j, and round the components to the nearest tenth of a mile an hour. Okay, so here's our pitcher, and he throws the baseball, and it's going in that direction. And we know that the speed is how much? Okay, so that what that's telling us, y'all, that is our magnitude, okay? So 65 miles an hour, and it says at an angle of 12 degrees from the horizontal. So I'm actually going to draw it so it looks like this, y'all. So that's my 65, I should really say, because it's going at an angle. And our angle is what? 12 degrees? Okay. So what we want to do is we want to write the velocity vector v at the time of release in terms of I and j. Anybody watch baseball? Yeah? Y'all see the game last night? Yeah? Pretty intense. All right, so let's take a look here, y'all. I'm going to scroll back over here and just remind ourselves that, look, again, we've done a lot of this stuff before. Look how we find the A and the B components. We take the magnitude times the cosine of angle to find the A component, and we take the magnitude times the sine of angle to find the B component. So I'm going to come back over here, and we're going to say to find the A component, we're going to take the magnitude, which is 65, times the cosine of 12 degrees, and to find the B component, we're going to take 65 times the sine of 12 degrees. Excuse me. I'm going to grab my calculator. I'm still in degree mode, so I'm going to go 65 cosine of 12 degrees. And it's telling me to go to 1 decimal place, or to the nearest tenth. So 63.57, would you say that's 63.6? And then let's do the same thing, but with the sign to find the b component. So we're going to go 65 sine of 12 degrees and 13.5. Okay. So the way we're going to write our vector v is going to be 63.6i plus 13.5j, because it's going to write it in terms of I and j. So there it is. All right, so y'all, we got one last problem to take a look at here. Let's see if we can't figure this one out. And let's see what's going on. Yeah, bearing's not my favorite either. But let's see if we can figure this thing out here. It says, okay, a boat travels 10 knots at a bearing of north 25 degrees west in still water. It encounters a current moving due west at 3 knots. Find the true speed to 1 decimal place in the direction of the boat to the nearest degree. Okay, so the velocity of the boat in still water is given by, okay, so let's take a look here, y'all. Yeah, VB is going to be the velocity of the boat, right? Okay, so what we're going to do here, y'all, we're going to try to write this thing in component form. Okay, so meaning we're going to write VB in AI plus the BJ form, okay? All right, so remember how we find the A component? Isn't the A component the velocity of the vector times the cosine of my angle? And the B component is the velocity of the vector times the sine component? Okay, so let's take a look here. So let's find the A part first. We already know the velocity of the vector is, in this case, it's the speed. So it's 10 knots, right? So we're going to take 10 times the cosine of, guys, remember the angle is always the angle formed with the positive x-axis, okay? So we already know that this here is 25 degrees, and that's 90 degrees. Isn't the whole angle 115? Okay, so this is a cosine of 115, okay? And the B component is going to be 10 times the sine of 115, okay? So the way I would write this part here, y'all, I would write it like this. I would just put 10 cosine of 115 degrees I plus 10 sine of 115 degrees with the J. And there's the velocity of the boat in still water in that A and BI form. Okay. Now, the second part of the problem says, what's the velocity of the current? So let's take a look, y'all. The current is moving what direction? It's moving westward at 3 knots, right? So if it's moving west, y'all agree it's moving to our left? Okay. So if it's moving to the left, wouldn't we say, let's see, wouldn't we say it's like an A plus BI form, y'all? Would you agree with me that I could write it like this? Negative 3I plus 0J, because it's not going up, right? And it's not going down at all. It's just the water is just moving to the west. Since it's moving to the left, isn't that in the negative x direction? Right? Because it's going westward. All right. Now, the velocity of the boat is going to be the sum of those two vectors. So remember how we're going to add these vectors, y'all. We're going to take this number and add them together. So I'm going to take 10 cosine of 115 minus 3. That's going to be my I component. Plus the J component is still going to be the sine of 115 degrees with the J. So I'm going to do this part right here, y'all, on my calculator. Move this over, turn it back on, make sure I'm still in degree mode. Yes, we are. So we're going to take 10 times the cosine of 115, oops, 115, right, and then we're going to subtract 3 from it, so minus 3. Look at my x component. Now I'm going to be going this, I'm going to be doing this to the nearest tenth, y'all. So would I write negative 7.2 or negative 7.3? Yeah, negative 7.3 I, right? Oh yeah, negative 7.2, sorry. You said that. My bad. Negative 7.2 I plus, let's do the j. So we're going to go 10 sine of 115. And that's given me 9.0 or 9.1? 9.1. Okay. So this is the sum, right? I'm going to write it like this. V of the sum. Okay. Now, if I wanted to find the magnitude, which would represent the entire speed, right? This would represent the entire speed. Remember, if I wanted to find the magnitude of this, y'all, I would take negative 7.2 squared plus 9.1 squared. And let's do this on our calculator. So I'm going to go, well, whether it's 7.2 or negative, when we square it's going to give me the same thing, plus 9.1 squared. I'm coming up with that. Then we got to take the square root of our answer. So to the nearest tenth, y'all, the magnitude is 11.6 or 11.7. What do you think? 11.6, right? So 11.6 is, this would be in knots, right? Because that was the units they were giving us. Okay, and we still need to find the angle. So remember what we said, isn't the tangent of our angle equal to b divided by a? So the tangent of my angle is going to be 9.1 divided by negative 7.2. Okay, so let's go second tangent inverse of, or tangent inverse here, I should have put, 9.1 divided by negative 7.2. Okay. And so I'm coming up with a negative 51.6, okay? So my theta is a negative 51.6 degrees. Guys, let me ask you a question. What quadrant are we in? Look at the picture. What quadrant are we in? Quadrant 2, right? So we wanted to write our answer in quadrant 2. We could just say, let's take 180 and minus 51.6 degrees because we are in the second quadrant. So 180 minus 51.6, and that's giving me 128.4. So again, think about what's happening, right? The boat's going in that kind of angular, at an angle boat. This is the actual speed of the boat with the angle. And because that current is moving the boat, right, the boat's actually moving a little bit faster because the current is moving it. So it's not just going at 10 knots, it's going at 11.6 knots. And it's not actually moving at 120 or 115 degrees, it's actually moving at 128.4 degrees, okay? And that right there, y'all, is 11.4. So I think out of all the problems we did today, this is probably the one that's probably the most challenging. But again, we were using the same ideas and the same concepts we've talked about before. You know, Pythagorean theorem, how do we find the x component? We take the magnitude times the cosine of the angle. How do we find the y component? We take the magnitude and multiply by the sine of the angle. So again, those ideas, we've already seen them before, right? So let me show you guys something else real quick, y'all. Let's see. We got some people at home watching. Good, good, good. Thomas, I see you're here. Okay, so y'all, first off, let me stop recording because that's the